In this video, I'll show you how to do logistic regression from A to Z. We will use an example from the book Marketing Research and Applied Orientation. The example is very nice. It's very simple. Of course, if you need to set your working directory first, I'll try to put a link in the description for this file that I used. And I'll also, of course, put the script, the whole script, on GitHub. So the table is like this. You have here the number of participants. You have the loyalty, which is the Y that we will try to explain. And of course, it has zeros and ones since it is logistic regression. So we will try to explain loyalty of a customer from his brand attachment or something like that, the product liking and the shopping experience. So these are ratings that have been given to customers, and they will, based on these, we will predict the loyalty they have for the brand. And this loyalty is a binary variable, so it's coded as zeros and ones. Of course, this is the main difference between ordinary least squares and logistic regression, is that the Y variable is coded as zeros and ones. So first, let me show you. This is in the book. This is nice. Let's use just the regular linear model to try to explain the loyalty through brand, product, and shopping as we have in the data. We summarize this example using OLS. What do we find is that brand actually predicts loyalty. However, if we use this model, and these are betas, of course, for the model, and we can just plug ones, which are the lowest values we have for example, for the brand, we have it's from 1 to, I think it's from 0, no. Yeah, it's from 1 to 7 for each variable. So if we plug these values in the model, what we will find is that we will find a negative value, since we have minus 0.68 for the intercept. And this doesn't make sense, since probability is always between 0 and 1. And if we plug higher values like 6 or 7 for brand, product, and shopping, we will find, since we have a very small intercept here, we will find values over 1. So in both cases, we will find values which don't make sense, which are counterintuitive for a probability, since the logistic regression predicts the probability of doing something or belonging to a certain group, for example. So that's why the OLS doesn't work. The classic linear model doesn't work. So we will move to the logistic model, and with the function we use is GLM, General Linear Model. We will just put the formula, of course. The brand loyalty is explained by brand, product, shopping, the data set, of course, and the family. This is what this is the main difference. We use the family binomial, since we are trying to predict a probability of zeros and ones. So this is why we use family binomial, right? So that's it, and then we summarize the model. What happened here? So I think yes, loyal to yeah. Well, I did some. I changed the name of the data set, so I think I'll be fine. Yes. So again, we have a brand which explains the loyalty of the customer only, and the other variables do not explain. See, we don't have p-values which are less than 0.05. So here the interpretation is really the same as what we do with the ordinary list squares. That's it. That's for the variables. But for the model, unfortunately with R, it doesn't give you if the model is overall significant or not. But we need to do some more. We need to code a little bit more. So what we will do is that we need to calculate this model chi-square. The model chi-square is something that is already in the model. We will it's the difference between the deviance. The deviance is simply 2 times the log likelihood, and the log likelihood is how the model is actually calculated. With times it times 2, and then there is we subtract the log model deviance, which is the unexplained variance, if you wish, if you compare it to logistic ordinary list squares, meaning that the model explained something and did not explain something. So there's something which is left, and what we are trying to do is to calculate how big is this difference actually. So let's name this model chi-square, and here we have 18, but actually it's just the difference between this null deviance here, which is in the output, minus 23. It's 18. So the thing is that this difference actually follows a chi-square distribution. If you study statistics, you know what a chi-square distribution looks like. So this difference follows a chi-square distribution with degrees of freedom. It's the same. We will just use the degrees of freedom with the null model, which meaning with only the intercept, and the residual model, okay? And we will calculate the probability, and the probability is 1 minus the cumulative probability with this chi-square and those degrees of freedom, right? So if we just get the answer, is just 18, which we already calculated. We have 3 degrees of freedom. You can look at and see them here, 29 minus 26 between the two models, and this chi-square model and the degree of freedom are significant, right? So that's why we calculate this probability. So we know now that this model overall is significant, in addition to the fact that the brand significantly predicts the loyalty, right? So that's it. For the R-square, to see the overall, let's say, quality or significance, or not significance, but the overall capability of the model to predict, let's say, the loyalty, I'll use a function which I found in the book, a very nice book by Andy Field, and he has this script actually that you can use, of course, from my own script, and just use this function, and it will give you 3 of the most famous and usually reported R-square measures, which are the Hosmer-Lemchow, Cox-Snell, and then Nagel-Kirk. I think this is the way it's read. So just use the function, and then you plug inside the function the model, since the function only works with the one criteria. That's it. So you have here the different, and usually what you report is 1, 2, maybe sometimes you can report 3 of them, but it gives you an idea of how good your model is. And in this case, for example, if we can summarize the 3 of them, we can say that overall the model explains between 44% and 60% of the variance in loyalty. So this is another step. Another step in using logistic regression is to, of course, report the odds ratio and the confidence interval. It's very easy to do. What you do is just you calculate the exponential of the coefficients of your model. The coefficients, of course, are these ones. The one for the intercept, of course, we don't need that, and the one for each variable. Of course, what we are interested here in is the one for brand, since it is the one which is significant, right? And if you find that the confidence interval has ones, like we will find in these 2, that means that they are not significant, of course, because contrary to ordinary least squares, normally we should not find zeros. But here we would not find 1, since this is the difference between a positive and a negative value with exponential. So we calculate the exponential like this. Of course, it's very easy, and we will be interested in this one I said, and this can be interpreted as 1 unit increase in brand increases the odds ratio of being loyal by 3.57 times. Well, this is how it is interpreted. Of course, we can also, as I said, calculate the confidence intervals and report them, of course, with our results. And as I said, we have ones in these two variables, product and shopping, which is not the case in for brand, of course, since it's between 1.62 and 11.37. Of course, we need to check some 2 or 3 things before we report our model. The first one is the multicollinearity, and this is the same as we do for ordinary least squares. And the idea, of course, is not to find any high correlations between the variables. Of course, we can use the correlation table, but it's very safe to use the VIF, much better. And usually, of course, values above 5 are problematic, which is not the case here. So there is no problem of multicollinearity between the predictors. We can move to testing the linearity. Now, this is something very important. What we do is just we add logarithmic variables with the predictors. So we just calculate those. For example, for brand, for product, and for shopping, these are the three predictors we have in the model, and we will just include them in another model. For example, as I named this model loyal model 2, and add the interaction terms between each predictor and its logarithmic value or logarithmic variable, and that's it. So we use these interactions in the model, and the idea is not to find any interaction term which is significant, as we found here. So there is no problem with the interactions. So that means that the linearity assumption has been respected, and this is something which is different as the way it is actually studied with normally the ordinary least squares. Normally with the ordinary least squares, we assume that each variable is linearly related to the outcome, but this is not the case in logistic regression, since the outcome variable has only zeros and ones. Sometimes, of course, it can have zeros, ones, and twos, for example, but it's not really how we calculate or how we test this assumption. What we do is that we need to not find that the interaction term is significant, and that means that this variable is linearly related to the outcome variable. That's it. So before we finish, we need, of course, to look at the case-wise diagnostics, and this is a very important step in every regression, of course, analysis, is to look at for example, the standardized residuals. So the function is very easy, of course, it's the R standard, and we can, for example, look at values which are above 2 and less than -2. Normally, we should find less than 5% of, this is the rule of thumb, is that less than 5% of the values are above 2 or less than -2. So that's why I'll use the function sum just to check how many I do have. And in my case, I have one case which is either above 2 or less than -2. So 1 over, for example, my total of variables is 30. That's almost 3.3%, which is less than 5%. So I'm okay in terms of large residuals, okay? I'll move to the distribution of the studentized residuals. Of course, I can also check the standardized residuals, but usually this is the best way of looking at residuals, is looking at the studentized residuals, which are residuals that have been standardized, actually. So normally I should find that they have a certain shape which looks like normal. Usually it's not really normal, but it should not be far from having this normal distribution. Well, the function is R standard simply, and you plug the model inside, and we'll check this histogram, which normally should have a normal distribution, but in our case, actually, it doesn't have really a normal distribution. And as you can see, normally the value should be between -2 and 2. We have maybe 2 or 1 or 2 variables, which values, which are really maybe far, that can cause a problem. We will check later. But the distribution is not bad. It's not really normal, but it's not bad. And you can report this, of course, when you talk about your results. Another issue we need to look at is the leverage. And here the function is the hat values. And normally what we look at values which are higher than 3 times the average leverage. And the average leverage is the number of predictors plus 1 over n. How many predictors we do have? We have 3 plus 1 over n, which is 30, and this is the average leverage, right? So what we need to do is just to time this, multiply this value by 3, and this is the, let's say, the cutoff, which we should not exceed, and this is 0.4, okay? So we need to look at values for the leverage which are above 0.4, and these can be, maybe they could be, for example, outliers, okay? So let's check these leverage values and see if we have any value which is above 4. We can do it here this way because we have only 30 values, which is very easy. And as you can see, we have no value which is above 0.4. So there is no problem here. We should not be concerned with the leverage, high leverage values. And finally, before we finish, we can also look at the df beta. And these are the differences in betas. Actually, if we take off for example, one case, and then calculate a new model, and then go back and insert the value and check if the beta has changed for this special case. And actually we can the R does it for each case. For each case it does it, and we normally look at values who have betas, difference in betas which are greater than 1. So the function is df beta simply, and it's the same as we do for all the different case-wise analysis, is just to plug the model inside the function. And these are, of course, functions which are basic functions in R. So let's check the values of the beta. Of course, we have beta values for each variable, and as you can see, we have no problem normally with those. We can, of course, check our data set as at all, because I added columns for each measure. And let's check the df beta and see if we have any value above 1. And as you can see, we have only one case, which is this one, which has a df beta which is almost 2. And as you can see, this one has also a studentized residual of minus 2.9, and it has a standardized residual which is large. I think this was the case when I used the large residual analysis, and I found that I had only one case which is less than -2. I think this was, of course, this was the case, right? And it has a df beta, and this could be an outlier, right? This could be really an outlier because it has a large standardized residual, and it has a df beta which is above 1. The leverage is no problem with this value, that's why we'll keep it. But we could, of course, and this is the best way to test if a value is an outlier, is just to get rid of the case and use the model again and check if the model has changed substantially. If it does, well, then this really is a problematic value, and it could be really an issue for concern. So that's it. I think we're done. These are all the steps you need to do to check for the model, to check for the R-square of the model, the significance, the odds ratio, the multicollinearity, linearity, and the case-wise diagnostics. If you have any questions, please feel free to ask them.